Mathematical induction is the proof technique built specifically for statements that need to hold for every single natural number, all infinitely many of them, without you ever being able to check them one at a time. The structure always has three parts. The base case shows the statement P holds for the very first value, n naught. The inductive step assumes the statement holds for some arbitrary value k, called the inductive hypothesis, and uses that assumption to prove the statement also holds for the next value, k plus 1. The conclusion then follows. By the principle of induction, since the base case holds and each case guarantees the next, the statement holds for every single n, from n naught onward, forever. There's also a variant called strong induction, where instead of assuming just p of k, you're allowed to assume p holds for every value from n naught all the way up through k, and use all of that combined information to prove p of k plus 1. The principle of mathematical induction states this formally. If p of n naught is true, and for every k greater than or equal to n naught, p of k implies p of k plus 1, then p of n is true for all n greater than or equal to n naught. This principle is logically equivalent to the well-ordering principle, the fact that every non-empty set of positive integers has a smallest element. Here's the intuition. Think of a long row of dominoes standing on end. The base case is exactly like knocking over the very first domino, and the inductive step guarantees that whenever domino k falls, it knocks over domino k plus 1 right behind it. Put those two facts together, and every single domino falls all the way down the line forever. Here's the trick that matters most. The inductive step is really just ordinary algebra, except you're specifically allowed to use one extra fact partway through, the inductive hypothesis. Always write out explicitly, by the inductive hypothesis, at the exact line in your working where you plug that assumed fact in. Worked example A. Prove that for all n greater than or equal to 1, the sum from I equals 1 to n of I equals n times open bracket n plus 1 close bracket divided by 2. Base case n equals 1, the left side is just 1. The right side is 1 times 2 divided by 2, which equals 1. They match. Inductive hypothesis. Assume the formula holds for some k, that is, the sum from I equals 1 to k of I equals k times open bracket k plus 1 close bracket divided by 2. Inductive step. Consider the sum up to k plus 1 instead. Split it into the sum up to k plus the one new final term, k plus 1. By the inductive hypothesis, this equals k times open bracket k plus 1 close bracket divided by 2 plus open bracket k plus 1 close bracket. Now factor out the common term k plus 1. This becomes open bracket k plus 1 close bracket times open bracket k divided by 2 plus 1 close bracket, which simplifies to open bracket k plus 1 close bracket times open bracket k plus 2 close bracket divided by 2. That's exactly the original formula, evaluated at n equals k plus 1, so the proof is complete. Worked example B. Prove that for all n greater than or equal to 1, 3 divides evenly into 4 to the n minus 1. Base case n equals 1, 4 to the 1 minus 1 equals 3, and 3 clearly divides 3. Inductive hypothesis. Assume 3 divides 4 to the k minus 1, meaning 4 to the k minus 1 equals 3 times m for some integer m. Inductive step. Consider 4 to the k plus 1 minus 1. Rewrite this as 4 times open bracket 4 to the k close bracket minus 1. By the inductive hypothesis, 4 to the k equals 3m plus 1, so substitute that in. This gives 4 times open bracket 3m plus 1 close bracket minus 1 equals 12m plus 4 minus 1 equals 12m plus 3 equals 3 times open bracket 4m plus 1 close bracket. Since this is exactly 3 times an integer, it's divisible by 3 and the proof is complete. Worked example C. Prove that 2 to the n is greater than n squared. This one comes with an important correction. Some sources claim this holds for all n greater than or equal to 4, but check that directly. At n equals 4, 2 to the 4 is 16, and 4 squared is also 16, an exact equality, not a strict inequality. So the claim as stated, starting at n equals 4, is false. Checking small values by hand. At n equals 1, it holds 2 beats 1. At n equals 2, they're equal, 4 equals 4. At n equals 3, it fails, 8 is less than 9. At n equals 4, equal again, 16 equals 16. From n equals 5 onward, it holds and keeps holding. So the correct provable claim is, for all n greater than or equal to 5 2 to the n is strictly greater than n squared, and that's the version proven below. Base case, n equals 5, 2 to the 5 is 32, and 5 squared is 25, and 32 is indeed greater than 25. Inductive hypothesis, assume 2 to the k is greater than k squared for some k greater than or equal to 5. Inductive step, consider 2 to the k plus 1, rewrite as 2 times, open bracket 2 to the k close bracket, and by the inductive hypothesis, this is greater than 2 times k squared. Now we need 2k squared to be at least, open bracket k plus 1 close bracket squared for k greater than or equal to 5 to finish the chain. Compute the difference, 2k squared minus, open bracket k plus 1 close bracket squared equals k squared minus 2k minus 1, which can be rewritten as open bracket k minus 1 close bracket squared minus 2. This quantity is positive whenever k is greater than 1 plus the square root of 2, roughly 2.414, which is certainly true for any k greater than or equal to 5. So 2k squared is strictly greater than open bracket k plus 1 close bracket squared, which means 2 to the k plus 1 is greater than open bracket k plus 1 close bracket squared. That completes the inductive step, and the proof is complete for all n greater than or equal to 5. Common mistakes to watch for. First, and this is the single most common failure, skipping the base case entirely. The inductive step alone proves nothing without a solid base case to anchor the very first domino. Second, quietly assuming the very thing you're trying to prove, instead of genuinely using the inductive hypothesis as a tool. That's circular reasoning, and it invalidates the entire proof. Third, off by 1 errors in strong induction, when a proof needs multiple starting values checked as its base case rather than just one. And fourth, exactly as we saw in worked example C, stating the wrong starting value for an inequality's valid domain. Always test a handful of small values by hand first, before committing to any particular base case in your final write-up.